Using calculus, let's help a soda company save money. At some point, there will be a challenge question, and the winner will get a shout out in the next calculus video. The objective is to use the least amount of material possible. But of course, we cannot just say make a smaller can, because there is a certain condition that the factory has to meet. Typically, a soda can holds 330 milliliters of soda. So this is the volume restriction. Speaking of volume, what geometrical object best models the can we have? I think we all agree it must be a cylinder of height h and radius r. So what dimensions give us the least amount of material possible? The key metric here is the surface area of the can. The surface area of a cylinder is 2 pi r squared plus 2 pi r h. So we need to minimize this function. But there's a problem here. Notice that s is a function of both r and h, and unless you're familiar with multivariable calculus, then you wouldn't know how to minimize a function of two variables. This is where the constraint equation for the volume comes in. The volume of a cylinder is pi r squared h, so we can use this to represent h in terms of r and plug this back into the surface area equation, resulting in a function of a single variable, 2 pi r squared plus 660 over r. So we now derive this equation and set the derivative to 0 to give us the critical point. We'll get 660 equals 4 pi r cubed, and then we'll solve for r by dividing by 4 pi, simplifying, and then taking the cube root. Now we need to verify that this corresponds to a minimum of the function, not a maximum. And this is where the challenge question comes in. The first person to comment 3 methods to verify that this critical point is a local minimum wins the challenge. This value is around 3.74 centimeters. And the height that corresponds to this ideal radius can be found using the relationship between the two dimensions. Plugging this value in, we get around 7.49 centimeters. So, the dimensions of this ideal cost-saving can is a height of 7.49 centimeters and radius of 3.74 centimeters. This will give you a can that holds 330 milliliters with the minimum surface area possible, so the least amount of material required to make it.